Hi folks, welcome back to Physics with Captain Rod. So this is just a follow-up video to my previous two examples about specific heat. So these examples were about these cannonballs that me and my buddy Jack made one day many years ago. And in the previous example, we calculated how many cannonballs we can put into this tank of water that has these dimensions starting at 10 degrees without bringing the water up to its boiling point of 100 degrees centigrade, given that the cannonballs were being dunked into the water around 327 degrees centigrade. And I think we found that 650 cannonballs it would take to bring this water up to its boiling point. So we have many short of that. We only actually ended up making 50 cannonballs. So now we know that we can do this fairly safely and the water's not going to give us any problems. It's not going to boil off or anything. So what we're going to do now is, assuming that we have 50 cannonballs to cool, and they're starting at around 327 degrees centigrade, we're going to imagine putting those 50 cannonballs into this tank and then calculating the equilibrium temperature of the water. Right? Now, in my previous video, we had calculated already that this tank of water, this tank represented about 880 kilograms of water. So, very similar to the previous example, when the cannonballs go into the water here, heat is going to transfer from the cannonballs to the water. So the cannonball's temperature is going to drop and the water's temperature is going to go up. Or in terms of internal energy, we would say that the internal energy of the water is going up while the internal energy of the cannonballs are going down. Now again, assumptions always important in these problems. So again, we're going to define our system like this. I'm going to put a boundary around my system. We are going to assume for this problem that no heat leaves or enters the system while these things are cooling, or while this process is happening. We're also going to assume again that the mass of the container here is small compared to the mass of the cannonballs in the water, so it's not going to have much of a thermodynamic effect. So those are important assumptions for this problem. Now, as long as no heat transferred across the boundary, then we can say the following thing, that the heat transfer for the lead plus the heat transfer for the water would add to zero, just like in my previous example. For the lead, the heat transfer term is going to equal mass of the lead times the specific heat of lead times T final minus T initial for the lead. All right, so there's your MC delta T term for the temperature change. All right, plus. All right, for the water, and again, we know now for sure we're not going to have any phase changes, so this is going to equal just mass of the water times specific heat of the water times T final minus T initial for the water. And again, the no energy transfer across the boundary is what allows us to say this sums to zero, that there's no net change in energy for the system. And that's just an assumption, but it's a reasonable assumption for this problem. Okay. What I'm going to do now here is just put in numerical values everywhere we have them. So for the lead, let's see, mass of the lead. We have 50 cannonballs total, and they were 5 kilograms apiece. So I'm going to use 250 kilograms. I'm going to put NCU for note consistent units, because otherwise I'm not going to have enough room in this on my little screen here. All right, specific heat of lead, 448. And again, that's in joule per kilogram degree centigrade. All right, T final we don't know, so I'll leave that. Minus initial temperature of the lead is 327 degrees. Plus, all right, mass of the water, that's around 880 kilograms. We calculated that in the previous video based on the geometry, based on the circular area and 0.5 meters deep. And we used the density of water of 1,000 kilograms per cubic meter. All right, specific heat of water, 4186. Again, that's in joule per kilogram degree centigrade. And then times T final minus the initial temperature of the water, which is 10 degrees centigrade. And then equals 0. All right, so putting in all these values, we see that these T finals, there's a T final on the left, T final on the kind of on the right here. An important thing to realize is heat transfer will occur until the water and the lead are the same temperature. So those T finals are the same. So now it's a matter of just solving this for T final. So I think what I'll do, I think I'll actually have my helpers here. I'll walk through this with me. So would one of you, and just give me the values that I asked for, please. Give me 250 times 448. Right. So this is 112,000 T final, right, times 327. $36 million what?
624,000.
Let's see here. Sure, I got the right number of zeros here. You said basically 36,600,000 thousand. Okay. All right. So there's that product distributed. We'll just do 3 sig figs. It's fine. Okay. Would somebody give me 880 times 4186? That's this product. 369 what?
3,696,238 TF.
You said 3 million?
Yeah, 3,696,238.
3,690 some thousand.
For 880 times 4186.
Yeah.
I got 3,630,880. Sorry.
You got 630,000. Let's get another opinion before I move on.
880 times 40. Oh, that's 86. 83.
Okay, 3,630,000, give or take. Okay, times T final, and then times 10. That's going to give us. Oops, I'm running out of room here. So that's going to give us now minus 363,000,000. Should give us one more zero, right? Times 10, and then equals 0. Right. So hopefully. Hopefully we've got all these values correct. If it's not, it's on my helpers here. Okay. So now give me 112,000. Oh, wow. Plus this value. And I can do that without a calculator here. So that's going to be, let's see, 1, 2, 3, 1, 2, 3. So that's 3,600,000. So that's still going to be, and I'm going to have to come down here a little bit. That's going to be 3,700,050. 0 T final. All right, double check that value. That should be 3,750,000, adding squiggly to squiggly, I believe. This is 100,000. That's going to become a 7. Whoops, 4. That's going to be a 4. Yeah, 3742. Oops. All right, times T final equals. Now, on the other side, we're going to have to put this term. Let me do this in red. This one and this one. So, and those are both negative. Somebody give me the sum of those two terms. Looks like to me 7,290,000. Whoops. Oh boy. Wrong number of decimals here. This was 36,600,000. And this was 36,300,000. 72. That's going to add to 72,900,000. Okay. And would somebody now please solve for T final by taking the 72,900,000 and dividing by the 3,742,000? This is why I like to just pause and get this stuff worked out.
194.81.
What's it come to?
194.81.
Got it? Oh, did I forget a zero on that? My apologies for that. I said 72 million, I know.
You're still missing a zero.
Yeah, whole bunch of zeros. 1, 2, 3, 1, 2, 3. Okay, there we go. I said it right, I just didn't write it correctly. Okay, give me the 72,900,000 divided by the 3,742,000. 19 degrees centigrade. Let's see if anybody else gets that.
At 19.3, 19.5, close enough.
Okay, we got a couple, 3 votes at 19. Yes. Okay, so let me just kind of round this up. And again, folks, for those of you watching the video here, sorry about the, it took a little while at the end. Usually I like to pause this and get these things worked out before I write the final answer, but, that's okay. Let me go over the highlights of this problem. So, again, important assumption here is that no energy goes across this boundary. That's really important because that's what allows us to write equals 0 on this right-hand side. And then we have MC delta T terms for the liquid, for the lead and the water. And then you just have to take note that the T finals are the same. Put in the numbers and solve for T final. I hope this video helps demonstrate those concepts. Have a great day.